In this video, we're going to go over coffee cup calorimetry and specifically the pre-lab calculations for our enthalpy lab. So this is not the exact lab that we're going to do, but it's a parallel problem. So we're going to start by going stepwise through how we would solve such a problem. In this lab, we're using zinc and a solution of copper 2 sulfate. The single displacement reaction that occurs, we will write out reactants and products balanced with phases. All right, so that'll be our first step in any calorimetry experiment. What reaction is occurring? We've broken down calorimetry problems into 3 steps, steps 1, 2, and 3. In step 1, we're determining the amount of heat involved when this amount of chemical is combined. So in order to do that, we measure a temperature change. We start out the problem assuming Q lost is equal to Q gained. In this particular reaction, the contents of the polystyrene cup go up in temperature. That means that energy is being given off from the reaction of these 2 chemicals to the water in the cup, and that water's temperature increases. So this is an exothermic process in which the heat given off by the reaction is equal to the heat absorbed by the water. Okay, so then moving things around and substituting in for Q of the water, we want to include the mass of the water in the cup, the specific heat, and the change in temperature. Now I have water written here in all these positions, but what we really mean is the solution, the copper 2 sulfate solution. And we are assuming that the specific heat of the solution is the same as the specific heat of water, and that the density of such a solution would be about the same as the density of water. Okay, that allows us to simplify what we plug into this equation. So we have 55 grams, we have our specific heat, and then our temperature change. Now for this experiment, the data was collected using a temperature probe and graphed for us. So we are going to get our temperatures, initial and final, from the graph. The initial temperature is very easy to determine. It's this initial flat line here, which I read to be 22 degrees Celsius. Now, because we're eyeballing this, we may have slightly different numbers here, but we do want to estimate the tenths place since we can read the ones place on this particular axis. Now, for determining the final temperature, the temptation is to just record the highest temperature that was reached. But we discussed that throughout the course of this reaction, the room was cooling down the solution in the cup. And so we lost perhaps some of the heat of the reaction was lost to the room as these, what do we have here? 3 minutes elapsed during the reaction time. So the way that we try to estimate the amount of heat that was lost and what final temperature we might have reached is by extrapolating that cooling curve back to the instant we mixed the chemicals, which is right about here. Okay, so right when the temperature started to go up, if it went up instantaneously at that time, it could have reached a temperature of 68 degrees Celsius. Okay, which is what I'm using for my final temperature. When you do this experiment in the lab and you use the lab data, you will have the equation of this line and you will be able to determine your TF from the equation of the line. And I'll show that to you at the end of these calculations. Okay, so we have our initial temperature and we have our final temperature. And so we just subtract those to get our delta T. And our calculation for Q of the reaction is negative, so it means 10,600 joules are given off when this amount of chemical reacts. Now that is not called the enthalpy of the reaction. That's just the Q, or the heat. The enthalpy of the reaction is determined by finding out how many joules per mole are released. Okay, enthalpy is a molar quantity, which means in step 2, we have to figure out how many moles of limiting reactant we had. Now in this problem, it's not clear what the limiting reactant is, so we have to determine that. So that's part 2. I took the amounts of each of my chemicals forward to find out how many moles of our copper product would be formed. So for zinc, that's just a matter of dividing by its molar mass. For the copper 2 sulfate solution, we use its volume and its molarity, right? Because molarity is moles per liter, to find out how many moles of copper 2 sulfate and ultimately how many moles of copper are then produced. We can see that this amount of copper 2 sulfate solution limits the amount of copper that can be produced, and therefore the copper 2 sulfate is our limiting reactant. All right, so now we know how many moles of limiting reactant we have. That's a 1-to-1 ratio. So we can just take this number and calculate enthalpy in our final step. We take our Q value, we divide by moles of limiting reactant, and I have 194 kilojoules per mole, and that's a negative number, remember, because this is an exothermic reaction. So those are the 3 steps in a calorimetry problem. Now, in this pre-lab and also in your lab calculations, you're going to need to do a percent error calculation. How close are we to the true or literature value? So that was given in the problem. And so our next step is to set up a percent error. Observed minus true over true times 100. Be careful of all these negative signs here. All right, negative 194 was my observed value. I subtract from that the true value or the literature value. All right, I get 24 when I do that. Positive 24. Over our true value, negative 218. 2 sig figs in my numerator give me 2 sig figs in my percent error. So what does this tell me? That my answer is a little bit low, okay, by 11%. The final bit of data processing that we're going to do for this lab is to propagate uncertainty. And it's been a while since we've done that. So I will just remind you that propagation of uncertainty is when you take your uncertainties from your measurements and you carry them through every calculation that you did until you get to the end of the problem. So essentially, you can make a table of your uncertainties. This is how I usually like to do it. And I just plug in the numbers as I used them in the problem. Okay, so let's take a look at that. So the first thing I did, I'm going to also put my work from the problem here. So let's see here what's going on. All right, the very first thing I needed was my mass of water. And I didn't have mass of water, right? But I had volume of solution. And based on density, that's going to be the same as the mass, okay, in grams. So I take the uncertainty, the value, 55 milliliters, the absolute uncertainty from the measuring device, and I calculate the percent uncertainty in my volume. And I'm going to put underneath that, I'm also going to put in parentheses, this also is going to correspond to the percent uncertainty in my mass, because that's what I used up here in my calculation. All right, we're going to assume that the specific heat of water has no uncertainty. And so now I have to include the uncertainty in my delta T. So I have my initial temperature's uncertainty, my final temperature uncertainty, and then I have the difference, my delta T. When you subtract 2 numbers, you add their absolute uncertainties. So my absolute uncertainty in my delta T is plus or minus 0.4 milliliters. My percent uncertainty is at 0.87%. I'm giving myself just one extra sig fig in each of these as I work my way through the problem. So that gets me all the way through these numbers, and then I multiply those numbers together to get Q. And when I multiply numbers, I add the percent uncertainties. So when I calculated Q, which was, oops, I didn't fill in the value here, negative 10,000 600 joules, I added the uncertainty in the mass and the uncertainty in my delta T. So my uncertainty in Q is the sum of those two, or 4.2%. All right, what's the next thing I did in my calculations? Well, I found my limiting reactant, and then I used my limiting reactant down here to determine delta H. Okay, so to find my limiting reactant, which I found to be copper 2 sulfate, I used volume again. Okay, so I have to include that in my table here, right? In order to find moles of limiting reactant, I took my volume of limiting reactant and I multiplied it by my molarity. Okay, I'll show you that calculation one more time. I took my volume of limiting reactant and I multiplied that by my molarity. Okay, and that's going to give me moles. So in my table, I now have moles of limiting reactant, and this 3.3% came from the volume that I used to do that calculation. Final step, I calculated enthalpy. Remember that enthalpy is equal to Q over moles. So I'm dividing those two quantities, which means I have to add their percent uncertainties, 4.2 and 3.3. All right, that gets me to 7.5. And remember, when your overall absolute uncertainty is greater than 2%, you round to 1 sig fig. So 8%. What is 8% of my answer for enthalpy? It's plus or minus 16 kilojoules per mole. And so my final representation is to show the box, my answer in the middle, and my range of uncertainty. Okay, so these are the same steps that you're going to take in the lab that you did. Okay, so you used the computer and the temperature probes to collect your temperature data, and you ended up with a graph, something like this. All right, and then you also have the following data, right? So you know your mass of magnesium, your volume of acid, your molarity of acid, initial temperature, and the time at which the chemicals were combined. The one difference in the lab that we did versus the pre-lab is that we have the equation of a line given to us here so that we can estimate, again, we want to estimate the maximum temperature that could have been reached instantaneously without the cooling of the room. And so the way we do that is we use our equation of the line. In other words, y equals, for this particular graph, the slope is negative 0.0159 times t. And so t is our x value, or our time, plus our y-intercept, which is 44.30. Okay, so for this person's experiment, the magnesium was added at 36 seconds. So you're going to do negative 0.0159 times 36 seconds plus 44.30. And that's going to give you your final temperature. Okay, and then you're going to go through that same set of steps that I just went through. So there will be some time in class tomorrow to ask questions, but what I recommend to you is really paying very close attention to the lab expectations for this lab. You have an entire page that takes you through the process of everything that you need to do to get full lab credit here, okay? In addition, you can look at your IB guide to writing lab reports. All right, and you can see how all of these different criteria will be graded that are listed on page 3 of your lab handout. So please come to class prepared to ask questions about this, and you can let me know how you're doing with your calculations. I hope the video was helpful. Please watch it as many times as you need to get comfortable with this. And let me know either by email or in class what questions you might have still. Thank you.